All right, so let's do a quick recap. Laptops. Let's do a quick recap. What did we cover yesterday? Where is my? So what we covered yesterday was, just pick it up. We should see. Let me pull up my lists. This thing is. What's wrong with me? So if you actually look at this, we were talking about, we had the first introduction, or rather we looked at MLIR. We sort of compared Pliron with MLIR, and then we took an example, and then we talked about the core data structures in Pliron, things like context and operation, etc. And then we said that there's quite a bit of abstraction involved over there. Anybody remembers, what context is all about? At least the abstraction that we use.
So yeah, context is the central data structure. It comprises of everything.
Right.
Yeah, and it uses that hash map kind of data structure where where the key value pair is there, but the key is not the actual key. It is basically the index. Yeah.
No, the key is not stored in the map.
Yeah.
Right. It's a data structure that's more dense. So it's just backed by a.
No, it's just a vector.
Vector.
Yeah. No, not vector of vectors, just a vector.
Just a vector. It's a vector. Why is it a vector of vectors? He just wanted to say that. It just sounds so cool.
Let us pointers of arrays.
I never said vector of vectors yesterday. That's what I'm asking. It's a vector, that's it. Oh, what you're trying to say is the context data structure contains many of those arena cells. An arena cell is a slot map. Okay. So we talked about this. An arena cell is basically a type alias for a slot map. Yeah, I think the conversation that I was trying to have with the author was maybe you want to name them separately or differently. But anyway, that's a longer discussion. But if you were to look at how, okay, we didn't change this part. Just give me 1 minute. Okay. If you look at the way the slot map works, you'll see this is what it looks like. So you'll have, one slot map for the operation type, types. For your operations in Pliron, you'll have one arena cell or one slot map. And then for regions, you'll probably have one. For basic blocks, you'll have one, right? Then if you keep this in mind, we have the index. That is, this index is not really part of the map, right? It's not part of the map. But what you do is that index is actually referred to as a PTR type, correct? Because if you remember what we discussed, we said that the index is usually called an arena index in the slot map. Okay. Right? We said that. And then we said the arena index is basically some sort of key that you want to use, but you wrap it inside this PTR data structure, because you want it to be type safe. You don't want to use keys for operations with keys for regions, or keys for regions with keys for basic blocks, because they are two separate storage containers, correct? That's one thing that we noticed inside the context. Yes? Okay, so, and then if you go further into the slot map, so slot map, is it something that is implemented in Pliron?
No, that's a different grade.
It's third party grade, right? The thing that slot map is usually referred to as is a generational arena, right? Generational arena is a little different. The reason for this is, if I have slots in my vector, and if I put this data structure together, which is this union kind of a thing, I can reuse slots. In a vector, you generally don't reuse slots, do you? You don't, correct?
Yeah.
With this implementation, you can reuse slots, because each slot is actually a union. Make sense? So as and when I have nodes as part of my data structure, I can go ahead and use it. When they are no longer required, I can pull them out. But if I pull them out, I don't have to reorder the entire vector. A vector is like what? It's like an array, except it's on the heap.
Yeah.
And then whenever you reach the end of the capacity of the vector, you need to like extend that.
Yes.
Right? Or you need to like create a new vector and copy all the elements in. That's a huge operation, right? This design does what? It still keeps your vec. It still allocates the entire space, but you keep reusing stuff. And in order to ensure that the reusing is safe enough, you start to say, okay, if I reused it, I will have a tag for that slot to say that this is a generation 2 index, this is a generation 3 index, this is a generation 4 index. That means this has been used 3 times before. So if you ever get a key that is trying to look up the previous value, because the key will have the generational value tag, and the map will also have the generational tag. All right, they'll compare both to say, okay, do these things match? They don't match. So if you have a previous slot that was already dropped or removed, you're not going to be, and the generation changed, you're not going to be able to access that data. It becomes free. Then you can put some new content into that vector. Make sense?
So it's just like a circular list.
Not circular. It's a vector.
Yeah, a circular vector.
No, a circular queue is where you have a head and a tail pointers, and then you keep wrapping those pointers around.
Reusing it.
You're using the queue. Now, that part is true. You're reusing the queue, but it's like a queue. This is not a queue. These are individual slots in the vec. You're reusing the individual slots themselves. Okay? You don't wrap around. That's what I'm trying to say. Like a circular queue. Got it?
Yeah.
Yeah? This stuff is important. Yeah, I already mentioned why it's important. It's because I want the store, wherever I'm storing these operations, let's say, I want them to be very efficient. I'll have many of them. I don't want to like blow up my memory. Okay? And I really want to be able to use some cache-friendly data structure. And a vector is a very cache-friendly data structure, right? Because it's all laid out in contiguous memory. Make sense? Now you understand what a generational arena is? Right? A generational arena, as it's implemented at least by the slot map, correct? It's a vector with reusable slots inside of it. How do you ensure that those slots are reused? You start using more information. Like I want to say, okay, we start assigning information like generation. The index will have a generation, so will the slot have a generation. So before you insert or before you read something from that, you check whether the generations match.
It will match with what?
With each other, right? The index is the key. And the slot map, the slots in the slot map have a generation. The index has one generation. So when you're going to use that generation, say give me this element, it's going to first look up the generation of the index and it's going to compare it with what the slot map has at that slot. That generation is the same or not? If it's the same, then yes. If it's older, then I'm sorry that you can't access that value. Even if it's there, we're not going to give you that value. Make sense?
Yep.
Right? That's exactly what I'm trying to showcase over here. So this is the storage type. It's a vector. But to index into slot 0 will contain the data and whether or not it's occupied. Okay, that's just a value, it's a U32. And then, like that, in this slot, each one will keep moving forward to say, okay, this one's vacant, this one's occupied, where is the next one? Like, if there's no data, then I look for the next free item, right? The next free slot in the slot map. That's how I know where will I be inserting my next item, right? So because I can have slots with this design, what happens is my slots will end up anywhere, right? So I need to know for that particular slot, is it vacant or is it occupied? If it's occupied, great. Then whatever operation I want to do, I can do on that. But if I want to figure out I want to insert a new item in it, then I need to know where the next slot is, which is free. And that's why this thing is a union. This data flag is a union.
Is the insertion deletion is taken care by the grid?
Yeah.
Okay. Then it's fine.
The reason I'm bringing up the slot map grid is you won't even deal with it. In fact, the author has gone ahead and called it arena cell. You don't care about it. You just do get and set and all that stuff. You won't do anything else. Okay. But you need to know why you're doing it.
Yeah.
If you don't know why you're doing it, you'll be like, right. Got it? Okay. So we covered this. This is the first part, which is generational arenas. That's part of the design that you see. Then, if ever you have some questions about it, look at the design evaluation notes. We covered the format of MLIR and Pliron. Okay? And then we covered arenas. What we did not cover yesterday were in a lot more detail is macros and how they make Pliron extensible. The extensibility part is primarily through traits. So traits and macros are what we will cover today. Like how exactly, do we create our operations, and then you can keep extending them to include whatever you want. The other part that we also covered is, if you go to this thing, you saw that we have the small example over here, which is this. Okay, we saw that we have this Cranelift code over here, intermediate format. We want to convert this to this.
Yeah.
Right? In order to do that, we saw what we do. We basically jump into the convert function, and then we see what's going on over here. Within this, there's a internally defined function, which is called convert and link. That's fine. But first things first, when we jump into convert function, the context is what? It's a Pliron context. What is the function? What type is it?
It's function type only.
Yes, it is. And what I'm trying to ask is, where does it come from? This is an actual, because we're trying to convert cliff to Pliron cliff, right? In order to do that, you need to provide a cliff function. That's the first point that you need to know. So we take that function, we'll come to this, we'll recap this again second. But you come here and say, what's the function's name? Okay? What's the function signature? What is the function's type? When I mean type, I basically mean its parameters type and its return types. And then using all that information, I go ahead and create the Pliron function type. Right? Then using the Pliron function type, Now I can create my full function operation.
In this case, we are only converting the function. That's why we are trying to like in ClickWire, everywhere there will be only function blocks or different blocks.
No, if you simplify, it's what it looks like. No?
There will be blocks.
Here there is a function block.
This is
there
one.
will be another block.
Correct. There will be other functions that look similar. Like, for example, which I think we saw yesterday. How happened to it?
I think we have problem with the mouse pad. Take a white
Need pad, I think.
Somebody give me a book. Not shit, man. I give it.
Open it.
Yes, but so saying this is a function. So if you go to something like, I don't know, let's say, what was I saying? Yeah. So if I go to Cranelift, and go to and I click this, and I click origin. Error docs. Docs. Wait, sorry. What the hell? Where are the dogs? Somebody eats the dogs?
Sir, straight go to file. Yeah.
Give me a minute. Hello? Yes, I'm good.
Pause.
Okay. Did you stop it or not?
It's recording now. Started.
Started.
So the pause button is.
It's already.
Recorded,
If you see
recorded,
here,
recorded.
recording. Yeah, you can see that.
Just give me a minute. I'll just stop this once again.
Yeah.
Start again. Alright. So what were we saying again?
ClickWire.
Yes. So we are saying that I wanted to show you one
Message for the dogs.
What happened to
You
the
can
dogs?
search.
Where?
Go to file on left side.
Docs series.
Where do you move dogs? They move the dog somewhere else. I think so. Where is it? It's a great here. Anyway, so higher end. If you go see this, for example, this is a C function. This gets converted to something like this. This is also Cranelift IR. So it will have multiple blocks. Each block will have instructions. The instructions are I multiply, I add, that's integer add, integer multiply, load, floating point promotion, stack load, all the stuff. These are cliff instructions. Okay? So you can have something like this. This is a more involved example because there's an if, else, branch, whatever, for loop is there here. Okay? In our case, it is simplistic. It's just a add two numbers. So it's like the simplest case.
It looks like a assembly only. No?
Yeah. These LLVM-IR and Cranelift IR, they're much closer to machine instructions than to your higher level constructs. So as I said, right, every translation from one IR to the other IR, you'll be getting closer and closer to machine code. And at every step, you are not going to have the same amount of information that you have at a higher level. Keep that in mind. Make sense? Okay. So now we looked at this. We said this is how you pull out all the function information from the Cliff function, and then you create a function type, and then you use that function type to create the actual function operation. The function operation will have what? It will have all this, right? It will have its function signature. It will have its body, which may have one or more blocks, and each block will have one or more instructions, or none, or no instruction. It's possible, right? Maybe an empty function. Make sense?
Yeah.
So this is what we saw yesterday. Any questions on this? All right. So if you were looking at this, we figured out the whole point of how do we convert from A to B, which is Cliff to Pliron, at least as far as the function operation is concerned. Yes?
Yeah.
Does that make sense?
Yeah.
So if we do that, then this part, I'll explain this part also because we touched upon this part. What is this part? There's a vector, there's a store that I'm creating, which bunch of vectors. That means not just the context. I want a bunch of vectors on the side for myself. This design might change. I'm just putting this together so that it's easier for me to do some implementation. So whenever I do a conversion, whenever I have converted something, apart from going and reaching out into the context store, I'm going to have my own little store on the side where I'm going to pick stuff from it. Okay? So that's what this is. So every time I convert an op, it gets pushed over here. A region is pushed over here. A basic block gets pushed over here. So far, makes sense?
Yeah.
Primarily, I need this data structure because of the entry block. Because it's, you'll see, when I was implementing it, I was trying to get the entry block and felt like if I just stored it in some place, it would be easier for me to pull it back out whenever I need it. Okay, that's why I'm saying this thing might change. Just keep that in mind.
So every function will have these blocks or
No, this is something that I'm doing.
you are
I am saying that every time I convert, if you give me a Cliff function, if I convert that to a function operation, that function operation will go and sit, apart from the context data structure, which is the main store that we use as part of Pliron, it will also come and sit here because I'm just pushing it. See this? I'm pushing it. So it's just a push. I do store ops push. That means store ops vector push. Okay? So the moment I do that, my operations are here. Get it? That's what we've seen so far. And after we do all that, now that we've got a converted Pliron function up, what we can do is we can try and display. Okay?
Yeah.
This display is going to be something very interesting because what you get for this display is when you actually implement it, each operation will implement the printable and parsable traits. Every single entity will have to implement them. Otherwise, you will not be able to see any of this. Make sense?
Yeah.
So, this is the recap of what we did yesterday. Yes? Let's just take a moment. Any questions? No? Revision done?
Yeah.
Going out and getting business is not more important. This is also very important. Okay.
yes, sir, that's something.
What?
I don't know.
When will we come to MIR? We come. Right?
Yeah.
Okay. So, with this context, now let's move to the other part that I mentioned, which is so if we come here, we wanted to see the second part, which is we saw the arenas part, we saw the basic IR format and stuff. We want to see more about the macros and the traits, the way these things work, because that's how a lot of the. So you saw the fact that for each function, I said there is a function signature, there's a block, and the blocks will have instructions, etc. But one of the things that you need to keep in mind is, in the implementation, you will see that when I'm creating the function op, I need to link all these entities. That means I have a block, right? To create the function op, I'm going to have to check to see if there's a block or not. I'm going to check to see if there's an instruction in the block or not. The moment I find a block and the moment I find an instruction, I have to say that this function has these blocks, this block has these instructions, and in this order. Correct? I have to do all those things. That linking needs to happen. If that linking does not happen, you will never be able to print, the entire function thing. Like, for example, you won't be able to print this. You will just print probably this. Yeah. Because that's all the function describes, the function op. But what does it contain? It contains this. So, these types, the operations themselves, they implement what are called linked list as a trait. There's a linked list trait, they'll implement that, and the containers like regions and functions, etc., they will implement the container list, which is it basically means that it is a container that will contain a linked list of items. Make sense?
Yeah.
So keep that in mind. This is this I spent a little bit of time because I was trying to figure out how the hell this will work, and this is the part. And again, Anand was asking me the question in the morning, like, this is going to take a long time, right, to get it exact. Like, if you just get the basics, the rest of it is just automatic. Like, if you get the relevant parts, like, if I'm able to take any function and convert it to Pliron IR, and if I can take any Pliron IR and convert it back to Cliff, and I've sorted those two things very clearly, then every other operation implementation or type implementation or attribute implementation is just to look at what you already have and redo the same thing. It's not copy paste, but it's using the same knowledge, you will implement everything else. Right? So in terms of time, only the initial piece is going to take time. The rest of it is going to be quick. Okay. In fact, my assessment, considering our workload, etc., everything, should be done in 3 months. I'm not kidding.
Is it?
You should. There's a reason why these workshops are.
Both part. Both converge.
Conversions are one, if you do one, other will be.
Convergent you'll anyway offload it to me only, no? First thing. तुम करो, उसके बाद हम आएंगे. इतना मारना तुम लोगों का.
Recorded नहीं था. Recorded.
Let it be.
Proof.
Proof. I'm going to put you guys in the internet, wait. That includes you also. So, my point is, I want you guys to, I will start anyway working on both sides of the conversion piece, so that I understand clearly how things are going to be moving back and forth. But, the point I want to make is, the moment we have those two pieces in place, like for example, if you look at his own implementation, the first thing that he's done is, apart from implementing the attributes, the ops and the types, he's got these two, from and to. From LLVM-IR to LLVM-IR. Implemented both of them. Everything else is just like a slide through for it, right? Right? Because the major thing that you probably need to do is done. Okay? So, right. With that context, let's move to the second part. Second part is, I wanted to show you, let's start with expand cargo, because we've already done this, you've seen it. We want to start with our own implementation, because our own implementation is simple. We have an add operation and we have a return operation. That's all we have. right? In our thing, we don't have anything else. So here you see return, we've seen this, and here we see add. Forget the sub. Sub is very similar to the add. Make sense? The other thing that you also see is there's something called register. Whenever you hear the word register anywhere, it is some sort of store. You're storing something. Register may register entry karo. Right? Same thing. This thing is whenever you create your own dialect and you create your own operations and types and attributes in that dialect, you need to inform Pliron the framework that these things exist. Get it?
Yeah.
That's why this register stuff is there. And there's a very interesting function over here that's parser function. We'll get to it later. It is there. Okay. So now let's look at the second part that I mentioned much more closely, which is we said we looked at this macro.
Yeah.
I said we'll get to this part a little later. Right? Which one? Derive of interface implementation. This does what? This macro at the end of it, if you were thinking about it, this macro will expand your code to say that your type will implement some traits. And in this case, a return operation is the terminator. That means for a particular program, that means a function, for any function, if you hit the keyword return, that function should end. It should be popped off the stack. Correct? That's what we're doing. Yeah. So we specifically captured that idea. In Rust, the whole point is what? If you have traits, if you have properties that you want to encode into your type, you probably make it a trait and say, okay, does your type do this? Does your type do that? Does your type have this? Does your type have that? Right? That's what we're seeing over here. And this is not like some simple thing. This is actually a trait. So if you go to the definition of it, you'll see it. Okay? It's a trait. And this is the simplest one that you can find. Okay? It has one method. And the implementation is okay. You can't get simpler than that. Because there's nothing to literally verify about a return state. It's return. There's nothing else to verify about it. Correct? But what's interesting is this thing that you see, this signature,
Dynamic dispatch.
it is the dynamic dispatch of a context of an awk, and then there is a context that's provided. So context will be there everywhere. Context is going to be pretty much in every call that you make. You will see context as CTX. Okay? CTX. Here, context is not being used, that's why it's like underscore, but that's fine. Makes sense? Okay?
In this, like return, if we are verifying, don't we need to verify we are returning the proper data type?
That part. Here, we're not discussing that at this point. Here, we're just saying it has to be the terminator only.
It has to be the
His terminator is not going to, that's the whole point. Very good question that you asked. His terminator is an interface that does not talk about what is going to return. His terminator is trying to capture the behavior that it will return. Okay, that's the first thing. You don't want to say anything more than that.
It will return just that flow.
Yeah. To your point, if you say that, what about the other part, which is whether you return the same type. Let me scroll down a bit. You'll see same operands and result type. This interface needs to be implemented. This is much more clear. Get it? And then you might wonder, okay, how do I say how many return types will I, how many inputs and how many outputs? How do I? There's another problem. For example, there's one result interface. One result. For Rust, it's always one result. Technically, you can always put all your results in a tuple and send that out, but it's always going to be one result.
Yeah.
Right? So there's no what's called variadic results or whatever that. Rust doesn't support it. Right? We don't support that. Makes sense?
That will be tuple. You can tuple in the same.
We can return two variables.
In group, no, you return.
Not,
No, different.
I can't really think of a language that actually does multi-return.
Multi-return नहीं करता है, tuple बना के वो tuple में set करता है.
I can't think of one. But I think there are languages. That much I'm sure. Anyway, then there is, so you can see each one of them, each of these interfaces is actually a trait. What do those traits do? Those traits tell you that your op does this, your op has this behavior, or your op does this. That's what it does. Right? That's the point of the interface. Now, with that context, if you were to look up, sorry, where is it? I'll go expand. Let's go look at an actual op. Let's actually first look at the simplest op because it's the simplest op. Which one is that? We like it. Let's go look at the simplest op. Right. So you saw that whenever we do the first expansion, which is the op macro expansion, we get this part.
Yeah.
Right? When we expand the second one, we get not just this, we get all of this. And also this, all this stuff as well, this clone and copy and all that stuff. We get all this stuff, right? So the second trait, if you think about it, has a lot more, that's hidden behind the macro, right? What is it doing is what I want to focus on today. Make sense? So the first thing that you need to keep in mind is, look at this and go like, don't do that. Okay? Don't do that. If you look at it carefully, with your knowledge of the Rust world, just observe the syntax and nothing else.
The whole thing is unsafe, huh?
That's the first thing that you should say. Yes, it's unsafe. And that's definitely a thing that you need to keep in mind. That's why partly it's implemented as macro. Okay, we'll talk about that. But first things first, you see that the isTerminator interface is basically an empty interface because the isTerminator trait only has one verify method that's already implemented. The default implementation is provided. I don't need to do any other implementation. It's empty. Okay. Then you have this. You'll see this. There are various reasons for why you will see this.
Constant.
Yeah, you'll see this. What is this thing called?
Understood.
Pattern. You'll see this pattern that you'll just call it some const, some name. Let it be a tuple, and then you put that in this scope. You're basically defining a const, right? But you don't care what the const is. But you want the const to be put in this trait, right?
Okay.
This is a common pattern that you will see when you're writing macros. And we have to clearly figure out why. Okay, but it should already tell you something. There's a lot of static stuff here.
Yeah.
Yes, to your question, why are we talking about unsafe?
It is linking to this link section.
Actually, let me stop here.
It's a static.
Global state, not mutable. The global state is being used.
That's why it's.
The moment you start thinking about that, maybe you want to figure out, okay, let's look at this. It's global state, which means I could have multiple writers and readers and things that are changing that state, right? That's one way to look at things. But if I asked you what is the type of cast to trait, go for it.
It's a
Lazy lock.
lazy lock.
It's a lazy lock.
It's wrapped inside a lazy lock.
Okay, what's the first, what is the, there are two things inside a lazy lock, right? What are the two things?
As a box,
The first thing is
One is the box
Yeah.
of,
dynamically allocated
not allocated, dynamic dispatch.
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 Dynamic dispatch,
it implements
These
Type
two
ID.
Sync, send, and
Perfect. What's the second one?
type ID and type ID. It's
Type
tuple.
ID and type ID. It's a tuple. Right? So far, that's how I wanted to think about it. Don't look at the macros expansion and say, what the hell is this? It makes sense. You have a lazy lock. Okay? I'll get to the lazy lock part later. You have some kind of data structure called the lazy lock, which is probably got two generic parameters. One is a tuple, the other one is a box that has, a boxed, dynamically dispatched, clonable any with send and sync. That means send and sync matlab
It can be like
shareable,
multi-threaded, yes, shareable.
syncable. Right? So by now you should know something that this stuff is talking about threads.
Yes.
That must be clear. And we are looking at static. Now to your question of why unsafe.
Because it's static.
So there's some thread stuff going on here, there's some static stuff here, so let's assume that it's still not, the one thing you should keep in mind is it's not global mutable static, it is just static.
Just static.
this what you're doing can use multiple threads.
Yeah, so we'll get to the part, and then this is the important context that I want to give you. Then, this thing, this static, the thing about statics that you already know is they must be initialized. You can't have like, if it's a global static, it must already be initialized at compile time.
Yeah.
Right? What if you don't want to do that?
Lazy.
You want to do lazy initialization. So that lazy initialization is what? Is what you see here. Okay? So this is a different thing, but I want you to focus on this.
This we have used in Rust code also, no? Lazy.
That's exactly why I'm trying to see if anybody connects it or not.
Yeah.
Except that it's not a lock
It's
in
not
Rust
a
code.
lock.
It's lazy initialization in the sense.
Initialization.
It's a standard lazy initialization that we're doing. There are no threads because Rust code is single threaded, not multi-threaded.
Yeah.
Right? Okay. But the idea is you want to defer the initialization. That means you don't want to initialize it at compile time. You want to initialize it upon first access. The first time you access that value, you want to initialize it. That's exactly what lazy initialization does. Alright? Why do you want to do it? Don't read.
Because of that static data. Static.
Shut up, don't read. Anyway,
It needs to be initialized.
I'm saying no. Why do you need something to? Why do you need to initialize something lazy? I'm saying you have the ability to do so. It's a static. You can do so at runtime. But why would you want to do it?
To give it memory when it is initial.
When you need it.
when you need
That's
it.
one way of thinking about it. That's fine. Anything else?
Whenever we create an instance of it, then only it will initialize it. That is why.
That's one. Anything else?
Already started.
Okay. There are three reasons for it that I've outlined. Maybe other reasons as well. One is the performance optimization. For example, if initializing the value is expensive, it involves a lot of computation. And then allocating a large amount of data. Then in both those cases, be like, okay, wait, is it absolutely necessary to do this right now? That means upfront, when I load my program, I'll have to set aside so much space, or I'll have to do the computation and then get this thing initialized. No, I don't want to do that. Only when I need it, I want it. Second, avoid unnecessary work. If the value is never used, you don't know if it's going to be used, right? Why even spend time initializing? Third, global state, which is what you mentioned. Right? That's our section. Global state. Lazy lock is often used for global variables or static data that need to be initialized lazily, safely in a multi-threaded context. Yep.
But when it is said that it has lazy initialization, what value is actually stored at the before it?
Yeah. The point is, don't think that it exists right now.
वो exist नहीं करता है.
Because whenever needed, then it will
No,
initialize.
because like in C, if you don't initialize any value, it's a static variable, you don't initialize it. By default, it has the value 0. It will not have any garbage.
You're saying where does it exist in memory is what
If when it is existing in the memory, some data is there. Now either it
Ah,
will be a garbage or
it
what
is-
that is.
That's the reason this is not like part of your stack or your heap, which is why you put it. You put it in BSS.
Yes,
static.
BSS. Even
Right,
static
BSS.
would be there.
BSS static, what you're saying over there is, I don't care what's there.
No, it's by default 0. I think.
By
So,
default,
by
0.
default 0.
Theoretically, it's supposed to be 0, but I'm not going to go and say that it has to be 0. You don't know which implementation does what. Some people might put another value in there. Or some people might not even initialize that to 0. But effectively speaking, this is a global static. So it's not going to live in either the stack or the heap.
Yes.
Right? It's going to live in a separate program memory, which is going to be static throughout the program's lifetime.
Yeah.
So there is separate memory. In that case, what exists over there is not. In other words, it's undefined when you actually have not initialized it. That's how you look at it. Unless you initialize it, you're not supposed to use it.
I guess like this implementation is like in C, if you are uninitialized, by default, it is written as 0, the value. But over here, memory will be allocated, but
That's
it will
not
be a.
necessarily true. If it's uninitialized, it's written as 0.
Yeah, it is.
It's not necessarily true. That's why you have undefined behavior.
That is for your
In C,
local variable.
local variables.
In the on the stack.
If you're saying only for static, it's uninitialized.
Yeah.
It's initialized.
Yes, yes.
The reason what I'm trying to say is, when you say it's static and stored in the BSS, I'm saying I don't know. Depends on what compiler and what you are trying to do, how it's implemented. But in most cases, you're right.
Yes.
Makes sense. So you could have your own compiler write it in such a, written in such a way that I don't want to use BSS because of XYZ reason. I want to put it somewhere else. So
That is again a special case.
it's a special case.
No, I feel they are not writing even that 0. It's saying that before you use it, I'm not going to do anything. But when you are using it, that time I'll write.
BSS, if you're only focused on the BSS
Yes.
part, BSS initialization is not done by the program. It comes to you whenever you load something, BSS is initialized to 0
Yes.
as an agent. And then whatever you allocate in there, link time is going to do all of that stuff and get it out. So you'll anyway have zeros over there if you're looking at the regular case.
Yes.
What exists over there is undefined as far as you're concerned until you initialize it. That's how you think about it, is what I'm saying. Make sense? In theory, what you're saying is right. There'll probably be zeros over there. But to you as the programmer, it's uninitialized.
Yes.
Yeah.
That's how you should think about it. Is what I'm
Yes.
saying.
Yes.
Make sense?
Yeah.
Okay. So far, so good. Any questions on this? We got lazy lock. So we looked at the first thing. We looked at the trait implementation, and when we saw that there's this other stuff happening over there, we're seeing that there's a global static that's being created, and that global static is usually called what? You know what no. The global static is usually called a cast to trait, the name of it, and it's a lazy lock. It's got 2 type IDs, and it's got 1 boxed in whatever. Okay.
Yeah.
Go to lazy lock.
This is the expanded output.
This lazy locks has a lazy thing in multiple implementation. We use lazy initialization.
Yes, yeah, you want me to go to lazy lock? Wait a minute.
It's a standard library.
Lazy lock is not something that we implement. Okay, but just so that you asked, I want to see. I can't jump in from here. I want to see where. I'm just trying to recollect. So I go to anything like an op. I go up and look for lazy lock. Actually, search across the thing. Yeah, I forgot.
Search.
And left.
Left file search.
And usually a shortcut for this, no? So, yeah. Okay. See this? So it's inside whatever. No, that's not mine. Okay. This is good.
The same file.
Same.
What the hell? I think so. Alright. You want to see this? Where is this?
It's a standard thing.
It's inside a.
Standard level.
Okay, instead of looking at it here, let's just go here and go look at the log. Okay, it's one of the same primitives over here. A value which is initialized on first access. This type is thread safe and can be used in statics. Since initialization may be called from multiple threads, any dereferencing call will block the calling thread if another initialization routine is currently running. Because there's a first time mutation, right? That happens.
Yeah.
The initialization is changing. You're changing it from uninitialized to initialized, so there's a mutation. You mutate for the very first time, and then you don't do anything with it, right? Mutate. So if you want to see what this damn thing looks like, that's what Sharat wants to see. He wants to see everything. That's what it is. He's just an unsafe cell. Yeah, nothing else. Or good. You don't ask me why is once and I'll go look it up. Okay? Get it? So
Yeah.
let me go back. Right, we're over here. Lazy lock. Lazy lock is basically, in lazy lock, what are we trying to initialize actually? We're trying to initialize these two type IDs and a boxed in is what is actually captured in here. Okay? So the first thing that actually happens is, I want you to read this later, not now, this part. The function name should give it away anyway. The function name is basically doing some type checking. Okay. So that's not the most important thing. The whole thing that you see from here, which is this whole thing, including this as well, is what you should be bothered about. You guys tell me what's going on over here. You're initializing? Okay. You break it 10:30.
Yeah.
Tell me.
They're initializing using the closure. That closure first, so they are initializing the type IDs.
Where's the closure?
This new
621.
620.
Achha.
To pipeline.
Okay.
Right. So the very first thing they are initializing the type IDs, and then they are
Creating
creating a
box.
smart pointer
Hmm.
with some lifetimes.
Some lifetimes. Okay.
Yeah. Cast to thread tick. But there is a tick A over there.
Go ahead, you're on the right track.
So they are using some lifetime.
Forget the lifetime. Don't get stuck up on that. Fine.
The passing a function
Towards
which returns
Returns
cast
option.
option which has
which takes what?
dynamic case takes
Cast to trait.
What the hell is on? What am I looking at? Is this Rust? I can assure you that is Rust. So the first part you guys mentioned is we're initializing lazy lock. That much makes sense? And the way you do it is you pass in a closure, you're right. So the first thing that you guys looked at was the tuple. Those are straightforward. There's the type ID, and you're going to basically initialize those two type IDs. But there's something very interesting about those two type IDs. By the way, every type in Rust will have a type ID. Okay, that's something that is part of the language. Like when you're working with types, you want to like clearly assign ID. This is the thing that actually does that. But in any case, in this scenario, you have two type IDs. One is the type ID for what type? Look at it. Add-on. The other one?
One
In result interface. That's the whole type. Remember, that's a dynamically dispatched type. Okay. Then that's the first thing. That's the first type. The second thing is the box queue. That means you are allocating something on the heap. You're putting something on the heap. What are you putting on the heap? Now that's the interesting part, right? You guys are trying to wonder what the hell am I reading?
cast to trait.
Just look down. What is cast to trait? It's a function. Are you sure it's a function? Yes.
Yes.
Then, if it's a function, it's also being named over there, right? So the question pops up: cast to trait as. Then forget there's a for tick a. He's saying that lifetime. That's fine. You forget that. There's an fn. Then there's an option. That looks like a function signature. Correct?
Yep.
Yes.
If I need to say
If you paid attention to the static name, it should make sense now.
So I feel that defining a function cast to trait there.
Yeah, that's there.
Which is a
Cast to
type.
trait is a function.
It is defined here, which takes dynamically dispatched any instance and gives out the option.
It's hard or close, but
But
it's
why
not
is
adding up.
on line number 629 there is a FN before that?
There is an as and an fn before that. What is that? Is what is the
Yeah.
question keeps popping up.
Yeah, so fn is a function type, right?
Yeah.
It's a full type.
Mm.
So cast to trait.
So let me just highlight what you're saying.
FN1 is FN.
Let me.
Traits.
Yeah, till there.
This is your function
Function
type.
type.
Typecasting there.
Yeah, so cast to trait is
You
type.
got it.
Yeah.
This is a typecast. I am trying to say, take cast to trait and try to cast it to this type.
Basically, naming is very bad. That's a problem.
No, they are giving as is there now.
Cast to trait.
Cast to trait as they are
And
given.
then for why is for is there? What for is
For lifetime. Because
Lifetime it is.
there's a,
Lifetime.
there's a the parameter that's being passed in has a ampersand, so you want to like tie them together. Okay, higher kindred types and lifetimes, etc. Don't get into that right now. Just know there's a tick over there. Fine. Make sense?
Yeah.
It's a simple cast. What does that mean? You can take a U8 as a U32, right?
Yeah.
That's a primitive cast. This is a user-defined cast.
Okay.
Make sense? The reason that will work is because if you come down and look at the signatures for cast to trait,
It's same like that.
it's freaking the same thing.
Hmm.
The thing that he wants to actually do is he wants to store a function pointer. He does not want to store per se cast to trait, because cast to trait is the actual function. It's a function item as is referred to in Rust. Function item has a type and has everything else. Function pointers don't really have that. Okay, it's a pointer to a function.
Yeah.
Get it? That's kind of what I mentioned. Okay. So if you see this, Pliron stores function pointers inside a box. Those function pointers implement a dynamic trait conversion function, which is din. Okay. So the whole goal that you're trying to do is, you'll see a lot of this lazy log stuff, right? This lazy log stuff is basically trying to do what I just mentioned. It's going to go ahead and collect these function pointers and put them in this thing called the trait casters thing. That means all the caster traits for the different types you have. You have IR op, you want to be able to say that I can cast this to the is-terminator interface, right? That thing is a function pointer, I'm putting it in here. All of them are going to be showing up here. The reason this distributed slice is there is because it's part of another crate. You're using a distributed slice crate that will allow you to basically say that, you know, I have this array, and wherever I define my function pointer, I can just add it to this array. That's why it's called a distributed slice. It's one array, but it gives me the ability to go ahead and define my elements that go into the array in different places. Right?
Yeah.
Makes sense?
Yeah.
Yeah?
This implementation is very similar to, again, interrupts. Over there you use function pointers for callbacks and
Correct.
store them.
Correct. That's one way of looking at things.
Yeah.
It's one way of looking at things. So that's what you need to keep in mind. And this pattern, you'll see it throughout. And here you might be wondering, hey, this thing is saying blocks didn't clonable any, right? But we are getting what is that? We are getting some din any, and then this thing and all that, right? We're not getting clonable any, right? We're getting something else, correct? So what's going on over here? Then what you do is you just scroll down a bit and then look at my notes. Okay. In here you will see that din any is something that you can implement for pretty much any concrete type. Okay. So the idea is that this is a type that can hold any type of data, but you do not know what type it is at compile time. You can think of it as a box that can hold any value. If you have a box din any, you're basically trying to say that there's something inside here that can be anything.
It's any type.
It's any type. Void pointer.
Yeah.
Okay.
Can be casted from.
It's possible. Then there's a din trait. This is a trait object, which means that it can hold any type that implements this trait. This is your usual din that you know. Like, it's a specific type that implements, it's a type that implements a specific trait. Right? So, here's what I wanted to show you. What happens with clonable any is, clonable any, if you actually go look at it, it's not showing up here, but if you go look at clonable any, it's actually, it combines three different traits. It combines any, downclone, and downcast. Alright? There's a reason why we're doing this. I don't want to confuse you with the downcast part, but at least I want to focus on the any part. Right? Because those two other things, you get it by default. Just assume that much. You get it by default. Any is what we're focused on. If I can take an object, if I can take a type and sort of typecast that to any, alright? When I want to get my original, or if I just get a din any, if I want to typecast that to my actual type, okay, I can do it because it's din any, right? I can go ahead and do it. But there must be a method for me to do that, right? So that I clearly get the right type that I want to get. Make sense? Yes? That's kind of what is being focused on over here. And the thing that I don't want to confuse you a lot is, we'll do that tomorrow, is where we look at the whole, how the traits pieces will add up quite a bit. But effectively speaking, note that the box din clonable that you saw, any, is what this is. This is just a helper trait that combines all these three. It allows the casters. The casters are nothing but cast to trait you saw. That is a caster. Any function that is able to cast from x to y, what are we actually casting? In here, we want to say that if we have an IR op, is that castable to this DIN interface? I want to figure it out at runtime. Is it castable or not? And this function will tell me whether it's castable or not. And if you go and look at this function inside its implementation, you will see that whatever you give me as input, in this case, the input is this, which is you're taking any, and you want to downcast that to IR op. Like this particular interface is what I have. I have a boxed in this interface. I want to be able to produce an IR op. This is what is helping me do that. Make sense?
Yeah.
Questions? Now, they're full of questions, but I don't want to ask them right now. There's a question. Yeah? Or just stare at it for a bit. Stare at it. Good. By the way, all of you guys have the notes, right? I shared the link, right?
I'm trying to think of a reason why they are complicating this lot of things.
Yeah, you're right to think about it that way.
Yeah.
You are right.
If they just wanted to cast it.
We are checking whether
No.
it is
Like again over here.
compatible or not.
Wait,
That's
just before you guys go ahead, very good question. And that's exactly what you need to debate. The reason is, unless you don't debate about it, then the whole why compiler engineering requires all this is a question. Like you will just simply want to use, register write, register read. Okay, that's not what this is about. This is about providing an abstraction to say that, look, I want to be able to figure this out. That's when I have a particular type, I want to see whether or not that type that I have, that means I got a function op. I want to know whether or not it implements this one result interface. That means the function op is something that I want to figure out whether or not it implements the one result interface, so that if I know that for a fact that it does implement it, then after doing my check, I will know for a fact that it does implement it. That means I can make an optimization over here saying that yes, this is one result. So basis that assumption, I can do something. You see what I'm saying? It's all about being able to query and being able to understand and analyze. That's the word I was looking for. Analyze your program, its constructs, and the interaction and the flow between them whenever you want. Like I have this right in front of me. I'm trying to figure out what does this, like, can I do, I want to do this optimization over here. Does it support, does it only provide one result interface? Because if it provides two results, then my optimization probably won't work, right? Or I want to do some flow analysis over here. I want to figure out what the lifetime of a certain variable is. If I don't do it, if I don't have any information to tell me for sure that this is true, then I will not be able to go forward. Get it? You are trying to programmatically extract information from the program. Like
The whole thing we are doing for just the return type, the is terminator type.
Correct. We're trying to figure it out. In this case, it's IAD op, so it's for one result interface. For is result for return op.
The terminator.
Is terminator for
terminator.
result op. Sorry, return op. Make sense? Alright? Here's my point. This pattern you learn once, it sears into your head, that's it. There's no more thinking you have to do. Okay? you don't see too much of this pattern. You will see this pattern once here, and this pattern will exist throughout. One case, you will have a lazy lock. The lazy lock will have two type IDs usually, and then it will have this function pointer that you will be storing, which is stored like a a dim trait. Okay. The object of that function, the dim trait, is to see whether or not if I can take that function pointer and use it to check whether the two type IDs that I have are castable to each other. That's the job.
Yeah.
Makes sense? And then you have distributed slice on top of that. The distributed slice on top of that is trying to say, look, I don't want to, it's like a convenience thing. I don't want to define everything here only. I want to define it in different places wherever I come across it. But at the end of it, when it's compiled, all of them just show up in one nice little array. And that's what the distributed slice macro does. It's a separate trait. Got it? Question?
This development, whoever developed it, twice,
Why was
he taken inspiration from any other company.
MLIR?
Just like this coding pattern.
This pattern is probably seen in many different places. I presume in the compiler framework as well, you see a lot
We
of
have
this.
multiple compilers in our site.
You would have taken some reference somewhere.
He's a compiler engineer, man. This is something that comes naturally to him. Right?
Yeah, because that will I was saying that you asked why is this so complex? This is complex because they are using function pointers. Where you are using function pointers, you are using callbacks. Callbacks you are using for faster access. So when there's faster access, your optimization. So their main goal is optimization. If they keep it simple, you don't get that.
Yeah.
So languages are different. Implementation is the same. Only they are changing this.
See, to answer your question, he's a domain expert. When I keep saying he's a compiler engineer, in his domain, he's spent quite a bit of time. He's seen all these patterns quite a bit. Even in C++, this type exists.
Yeah.
This pattern will exist.
Correct.
Okay. The thing is, it's much more simpler here to understand. If I try to read the same thing, I'll be like, correct me. This is what I was looking at in the LLVM code. I'm like, nahi hoga. Nahi hoga. Okay, there's no rocket science over here.
Yeah.
You just have to trust your skill in understanding Rust. Because you guys already have it. You know what a function is. You know what a function pointer is. You know what lifetimes are. You know what din is, which is dynamic dispatch. You know what tuples are, and you know what a lazy lock is. So you just apply that, and you should be in a position to say, yeah, I know what we're doing over here. But the question is why, right? That question is important. You've already figured out what you're doing. The next question is why, and that you're just beginning to get a feeling for it.
And what is the map they are using for? 641.
641.
It's a map.
Map is a function, right?
It's a function on a vector.
So,
or something like that.
If
on
you
a,
take
on a iterator.
yeah, it's on a something like not just an iterator. This will return an option. This will return an option. Okay, downcast ref will return an option, and then whatever you have in the option, replace it with this
What's sending that to map?
map.
With
Map will go ahead and do this,
So that's a closure.
and then it produces this. Right.
Why doing casting there as
S as line one resolution first. Or
Yeah.
line 641.
You want to do it. So whatever you get as S, whatever you get as S, whatever you get as S should be castable to this. That is my proof.
And that map will return.
Yes.
That will return. If it's castable, that's my proof. Chalo return.
you're checking that.
The S as either the type check should fail. If it fails, it's gone. Making sense?
If we are able to typecast,
If you're able to typecast, then yeah, that's correct. Samjhan?
then it will return S.
Then otherwise it's going to be a this thing, right?
Yes.
Make it sensor,
Yeah.
take it the break,
Yes.
If it is function.
and We have better faces. Stop recording.
No, not